Ladies and gentlemen, it's a pleasure to be here on behalf of MAPE, presenting what I hope to be an interesting presentation. First of all, compliments to a very professional arrangement here today, my first Latvian Concrete Day, hopefully not the last. Also compliments to the translators, who I had the pleasure of listening to from Latvian to English, so I'm grateful that I can do this in English also. So, as said, my name is Sven Henrik Norman. I am the Global Product Manager for a product line that have what I strongly believe is a very important part of the solution for what we have been talking about today. It's an admixture, and I will go through one of its application areas, which is recycled concrete aggregates to be used in new concrete production. The background is, as you probably are well aware, that natural sand is starting to be a depleted resource, regionally and globally. When I joined the business some 30 years ago, natural sand was still available in Sweden, my home country. And then gradually, in the end of 90s and 2000s, less and less natural sand quarries came about. And now it's a global issue, and very pressing issue in some regions of the world where they have intense construction activity, as India, for example. Another aspect of this is what we have been listening to, very interesting presentations today, the increased sustainability focus from government initiatives, from corporations like Schwenk, Heidelberg Materials, who have really, in the last, let's say, 15 years, come with big focus on sustainability. So the answer seems to be circular economy, how to reuse our resources in a better way. This is cost-driven in many ways, which is good, because that means people come up with engineering, innovative solutions. And it's also, as we heard, carbon footprint driven. We need to reduce the carbon footprint. And I've seen only in the last 10, 15 years that the whole value chain has been improved. If we start with recycling, when you demolish a concrete building, and I'm sure you have seen how that was done 10, 15, 20 years ago, and how it's done now with a much better sorting. You take out the concrete, you take out the rebars, the timber, plastics, etc. are separated. So that's the real start. Also, legislation. Equipment should be in the middle there, where much more modern equipment provides a raw material that is much more suited also for concrete aggregates. And then the certification of these aggregates are becoming better and better, and standards are improved, or is now allowing higher levels of recycled concrete to be used in mixed designs. There has been advancement in all these areas, and particularly, I think, well, from my point of view, chemical admixtures have developed rapidly. When I worked with manufactured sand in Norway some 10 years ago, I wish I had the admixtures that we have today. It would have saved a lot of water and a lot of cement, I can promise you. But so this is where let's say the backdrop, the background, where there is a drive towards using recycled aggregates. But there are challenges. Let's not kid ourselves. It's not an easy material to work with if we compare it to virgin materials. The higher water absorption, you have probably seen and experienced yourself, but also the uncertainties of pinpointing exactly what is the water absorption. The test methods that we use in our standards today are more or less based on from the 1940s, 1930s ASTM norms with testing natural aggregates. This creates an uncertainty, which we hate. When we want to make good concrete, we hate fluctuations or variations. We have also seen, when using really high dosages, let's say over 50%, that air content seem to be accelerating. So if we do nothing, if we just replace the aggregates from natural to recycle, we will see rapid slump loss if we don't do anything about water absorption. So the concrete can look very nice when it leaves the ready-mix plant. Half an hour later, it turns up at the building site, and it's not flowable anymore. This is a problem. If we have no control of the air content, we know for a fact above 5% air content, our strength is greatly reduced. And this is particularly active in the fine fraction. And if we try to use normal PCE admixtures to counter this, we need to dose them in such a high amounts that the stability then becomes a problem in the concrete. Slight variations in the moisture content, then we can have a separated concrete. Again, if we then just try to add more free water, well, we talked today about the carbon footprint, etc. We will have to use more cement, and then we are losing in environmental what we have gained in maybe using recycled aggregates. So sorption is really the key here, to get it under control and learn about it. Because sorption, as we know, affects the water-cement ratio. And if we have uncertainties about the water-cement ratio, well, we will have uncertainties about strength, durability, and workability. If we add to this, there is some lag in. If we add then variations in air content, again, we have too much variation. Sorption, I use the word sorption because we need to look at the two, let's say, main types. Absorption, where moisture is taking in through larger pores in the aggregate material, being absorbed, and adsorption, which has more to do with surface areas. So the finer the particles, the more surface area per kilogram. This is a known fact, but we need to study and separate these two aspects, and we can just call them sorption as a common name. So our solution is a product we call ReconAg, and we define it as a microphase retention system. So it was developed for a number of challenging raw materials. Clay-bearing sand, so we've had applications in Italy for this, local sands with high clay content. Manufactured sand with high fines, which we see a lot here in the Nordic areas. I know from Sweden we use a lot of granite crushed sand with high content of free mica. And recycled concrete aggregates, which is becoming more and more, let's say, interesting from several points of view. Again, discussions on circular economy. But also, actually, binders or, and secondary cementitious materials like calcined clay. So there are elements in this system that we also use in our admixtures directed more at binders. But today we focus on the, let's say, aggregate-based products. So microphase retention system, with microphase I mean the matrix, the water, the cement, and the fine particles, very fine particles coming from the sand. So we have two phases here. First we have absorption control. We do an initial shielding, or the polymers do for us. So it prevents large parts, not all, but it prevents large part of the water to be absorbed or adsorbed into the aggregate material. This means in that water we have PCEs. We have our normal. This system works together with superplasticizing admixtures. So by preventing the water, we also prevent the PCEs from being absorbed into the aggregate. Second is something we call adaptive polymer structure. And I'm not a chemist, so I just invented the name. But what it does, it's acting on the increased alkalinity that will happen during the hardening of concrete. And then the polymers that initially were acting as an initial shield, they now become a complementary PCE. So they extend the workability. So this is a two-phase system. So what we see, we make these claims based on a number of successful applications. So the graph here is a typical example of where you have a very demanding raw material, and you see a typical slump loss over time that is quite dramatic. But when you add the ReconAg technology to complement the conventional PCEs, we see a much slower drop in slump. So these results are proven, the positive effects on sorption control, and we let the free water and the PC admixtures, they stay in the cement paste for longer. This is the basic function of the admixture. So we extend the workability. And we also see that we have better control of the air content. So I'm going through two project examples. I think I'm doing well for time, I think. So we'll run through, there's a lot of data here, but I have two specific examples where we have used ReconAg. First one is a Norwegian project called Milbet. It's a producer in north of Norway called Nordland Betong. They wish to produce concrete with more of their recycled aggregates, and the recycled aggregates came from their waste streams, when their own production of paving stone, and the second waste stream is from the demolished Bodø airport. They are now building a new airport in Bodø, so the old runway needs to be chewed up, and that is a great resource for recycled aggregates. So the material that we used, we can see on these pictures here, a 0 to 4. You can see the pictures how let's say porous they are. The 4 to 8 looks like this, and the 8 to 22 is a recycled concrete aggregate. As you see, the cement paste sticking on the larger particles. Mixed design, we use a C3037. Heidelberg cement, Norcem standard FA, water cement ratio, 0.52. So we made a reference with 100% natural and one with 50% recycled concrete aggregate. We used our normal Dynamon plasticizer with this microphase retention system. Slump was with the natural, quite normal, let's say. 100%. This is now just as a reference test, natural aggregates altogether. Then second test was that we replaced 50% of the natural aggregates with recycled, and same slightly higher dose of the admixture, but you see that what I just described happened. The slump died after a very short while. So by then adding 0.5% of the cement weight with ReconAg 90, you see that our slump life is very, very similar to the reference with all natural. So that's quite a remarkable effect. So we can look at it from the picture point of view. This is the reference. Even we have a direct slump loss when we are not using ReconAg. When we're adding ReconAg, we have a spread here that is very similar. Again, after 30 minutes, you see the reference 2, let's say, already a drop in slump, and then we are continuing with a good slump life for after 30 minutes. After 90 minutes, there wasn't even the idea. It's pointless to take a picture, but with ReconAg, we managed to be very similar in the slump. Compressive strength. We see that by replacing with 50%, we gained strength. And here I would like to, let's say, make a kind of a disclaimer. I'm not, in some cases we have seen that recycled aggregates add to the strength of the concrete. My suspicion here is that you see the green ones, that's when we're using ReconAg, and I talked about air control. I think the difference in strength can be attributed to that there is much harder to control the exact water absorption with recycled aggregates than with natural. So what is the real water cement ratio here? It's a little bit uncertain. And also, when you see the strength gain between the blue and the green, that means that when we add ReconAg, we probably have slightly less air, so a stronger concrete by that. So that's all I can comment on those results. We then tested 84%, so we had a similar mix design, but we increased the replacement of recycled aggregates to 84%. Again, same admixtures and standard FA cement. Here, the slump is, again, kept alive really well when even with 84%. Compressive strength and air life. Yellow is the natural aggregate from 7 to 28 days. And ReconAg, where we also increased a little bit the defoamer. So we tweaked the formulation even to keep, because we noticed, because of the air content, the reference was totally normal, 0.5 to 1.2%, and we came to that same result, but we had to look at the formulation slightly, because at those high levels, air can become a real problem. So now to the jewel in the crown, let's say, for our project examples. It's our own R&D center. We recently were inaugurated by our owners and by Prime Minister of Norway. 1,000 more square meters of R&D center in Sakstua in Norway. And we thought, well, it could be a good place to put the concrete floor with recycled aggregates. So we looked at the Norwegian standard, what is possible. Norway has actually been in the forefront, in my view, in the Nordics with this recommendations for low carbon concrete and the different classes. So we aimed for the low carbon class plus, where we should be somewhere around 160 kilograms per cubic meter. That was our aim. And the choice of raw materials was a local Dynamon product, ReconAg 90, and our system for shrinkage reducer and expanding agents. We had washed recycled aggregates from an environmental park, concrete aggregates, also crushed. This was a SEM 3B from Schwenk that we used, and some microsilica. And part of the coarse aggregate was also a slag product from Eramet in Norway, a 10 to 22 millimeter. So this is just a picture of the aggregates, how they look. And that slag has quite a striking green color. So from a polished point of view, it was exciting to see what we could achieve. Mixed design here, I think we don't have time to go through, but those mixed designs can be made available to you if you wish so. So the job itself was made in 2 days. 2 areas that was polished and sealed, and in the office area we added our own floor system for office space, and we have the supplier Beton Öst. They market their own. They are marketing their own concrete mixed design. So we call it the Markbekrit system. They call it Done Fugefree. So. Challenge for the interpreters here. It was fiber reinforced concrete with shrinkage reducing agent and expanding agent, as I said. So how can this be a challenge? Well, low carbon concrete plus, first of all, very low cement content in the beginning. 100% recycled aggregates. 30 kilograms per cubic meter of steel fiber. And 1 hour transport. So I would call that rather challenging in any case. So how was the result? First load on site, after 1 hour, turned up with a slump of 230 and a spread of 400 millimeters. We pumped 145 cubic meters without any issues, and not our own words, the words from the project team, and that this would not have been possible without this admixture. So we were very, very happy and proud of the result. I think we can call it green concrete in both the literal and in any respect. And the result for GWP is that we achieved 157.3 when we used recycled concrete aggregates as the coarse aggregate, and 158.6 when we used the slag product. And the sample here is, of course, with the polished slag. So this is including all admixtures, not the reinforcement. Yeah, that's the end result. And just to conclude on that project, the hardening, we met the requirements for compressive strength by long shot. We tested, we put samples on site and we put samples in our lab in 20 degrees. So just to compare, and we met the 45 MPa in both cases. So to come to a summary of all this, recycled concrete aggregates absolutely can be challenging for workability, and I think it's important to think about ambition levels. What do you want to do? Is it a project where you have 10 to 15% that you want to replace from natural and go into recycled? Then the problems are much smaller. But in some cases, cases I like is those challenges where somebody wants to do like 100% recycled or so. If there is a cost, if you can save cost, why not try to use as much recycled aggregate as possible in the right application? Obviously, you always have to look after the exposure class, etc. But it can be challenging for workability, and also in high dosages. Not talking again 10 to 15%, but 50 and above. Really take care of the air content so that you are not getting a nasty surprise by 8 to 9% air, and then you lose your strength on that. Again, I think we have shown that our product has positive effects on those two challenge areas, but further research is obviously needed. I think we need to understand absorption mechanisms even better, and Roland's, with your work with NTNU and DTU in Denmark, and there is a lot of exciting research going on, and how to study and how to find new methods to define what is the water absorption, not only with the old methods based from 1930s. Really look at more advanced ways to track sorption, because if we can track sorption, we can also develop even better admixtures. I think also another that has been touched today is recarbonation. I think there is few materials that are more suitable than crushed, demolished concrete or other types of recycled aggregate containing calcium compounds. Of course, today still it's quite expensive to accelerate the recarbonation. The big investments, not something you do with in your own backyard, let's say. But we see some really interesting initiatives from the big, let's say, the big groups, Holcim, Heidelberg Materials, Schwenk, etc., on how to utilize this recarbonation potential, because it also improves the properties of this aggregate. It becomes more dense, and so it's a real win-win situation. But we need more research in that field, and we are at MAPEI, we are looking into our part of that. And yeah, with that, I thank you very much for your attention, and yeah, thank you.